Okay, I want to talk a little bit about the energy changes as you go from a circular orbit at distance r1 to a circular orbit. And let's put the word circular in there, at least abbreviate it. Circular orbit at distance r2 from the planet implicitly. Okay, so here's the planet. And here you are at distance r1. And you're in a circular orbit. So let's attempt to make some sort of a circle. Okay? And you're going to change orbits, and you're going to change somehow to circular orbit at r2. Now, it's very interesting what you have to do to get from a circular orbit at r1 to a circular orbit at r2. But right now, we're just going to look at how much energy change there is. So here's r2. And now we have a circular orbit here, draw part of the circle. Okay. So how much energy do we have? If we got mass m, so you should pause. Tell me what the kinetic and potential energies are at R1 and at R2. And of course, we also want to see the total energy. Total mechanical energy. Okay, well, what do you get? At R1, the kinetic energy is 1/2 G big M little m over R1. At R2, the kinetic energy is 1/2 G big M little m over R2. Potential energy is negative big G big M little m over R1, or negative big G big M little m over R2. So the total energy is negative 1/2 big G big M little m over R1, negative 1/2 big G big M little m over R2. Now, change in kinetic energy, change in potential energy. Okay? What's the change in kinetic energy from R1 to R2? First of all, is it positive or negative? Work this out. Think about it. Okay? And we're assuming, of course, that R2 is greater than R1. Make that explicit. It's kind of implicit from the picture, but pictures don't always represent things exactly the way we intend. Okay, so what do you think are the changes in the kinetic and potential energy? Okay, well, positive or negative. Does the kinetic energy go up or down? Well, R2 is bigger than R1, so that this has a bigger denominator, meaning the kinetic energy here is less than here. And this obviously means that the satellite slows down. Say negative, satellite slows. Okay? What about the change in potential energy? Well, you've got to be a little bit careful. R2 is bigger than R1. So the magnitude of this potential energy is greater than the magnitude of this potential energy. But of course, this is negative and this is negative. The negative number of greater magnitude is less than the one of lesser magnitude. So potential energy change is positive. Now it should be obvious intuitively that the potential energy increases because you're moving against the gravitational force. Increases your potential energy. So we have a negative change in kinetic, a positive change in potential. And of course, if you think about it again, the potential being negative, the kinetic being positive, and being proportional means if one of them gets bigger, if one of them increases, the other one decreases. Okay? Now we could certainly write out the expressions for the kinetic energy change. Kinetic energy change from position 1 to position 2, from orbit 1 to orbit 2, is the kinetic energy at R2 minus the kinetic energy at R1 and I'll factor out the 1/2 G big M little m over, well, 1/2 G big M little m. So factoring out the common factor here, we get this 1 over R2 minus 1 over R1. And again, we check this out. If R2 is bigger than R1, then this number is smaller than this number because it's a reciprocal, meaning, again, that you're subtracting the larger from the smaller, you're going to get a negative. So I'll make a comment. This is negative if R2 is greater than R1. Delta PE from 1 to 2. Well, I'm going to skip the intermediate steps so you can write it out as well as I can. And there's no 1/2. Should learn not to talk and write. Looks just like this one except for the 1/2 and except for this being negative. Now since this is negative, if R2 is bigger than R1, this is smaller than this, so that you're subtracting a larger from a smaller, and you're going to get a negative, but you've got a negative here, so again, it's positive. So if you're going from a closer orbit to a further orbit, you're increasing your gravitational potential energy. You're losing kinetic energy. Now there's one somewhat confusing thing, and I want to address this misconception. What you have between orbits the change in kinetic energy is emphatically not equal to the negative of the change in potential energy. It is true you're increasing potential energy and you're decreasing kinetic energy, but those changes are not equal in magnitude. So the change in, I don't think I improved that, did I? The change in kinetic energy is not equal to the negative change in potential energy, as it might seem if you carelessly apply the conservation of energy. Okay? Now, this is true if the work done on the system by non-conservative forces is 0. The implication of that is you can't get from here to here without non-conservative forces exerting we're doing how much work. So, the question I'm going to raise here is, changing the work done by non-conservative forces on the satellite equals what? From the first orbit to the second. We'll address that in the next clip, but you should think about that before you look at the clip.